Hello everyone. This is problem number 4 in the series of problems that I've been doing on mesh analysis, specifically for circuits having coupled coils. Let us try to see one more example so that we can consolidate the concepts. Here is a network which has got 3 inductive coils, and they are mutually coupled in a particular manner as indicated by the dots. And all we need to remember at this point of time is how to write KVL equations and how to understand the dots. As I've been telling, dots indicate the polarity of the mutually induced EMF. Similar dots near coils suggest that those coils are mutually coupled. It means current through one coil is capable of producing EMF in the other coil. It is as simple as that. Now, how to write the mesh equations for such a network is the question before us. We've been given with this network, even the currents have been shown, the clockwise currents, otherwise also we assume clockwise currents. We have an voltage source conveniently. Now we will write the equations. So we've been practicing a method wherein we are trying to indicate or represent all the mutually induced EMFs by dependent sources. That way I presume it is simple to understand and comprehend. Alright, so I'll try to rewrite the network now with all the inductors having their dependent sources, or in other words, mutually induced EMFs represented by dependent sources in their path. Alright, so let me write the network with the dependent sources. I'll try to I'll rewrite the network instead of copying the network. I found that to be much easier, though I may take a couple of more minutes than necessary, but then I feel that is convenient. This is my L1. So how many dots are there near L1? L1 has got 2 dots, one in the form of a circle, another in the form of a triangle. So obviously I need to write 2 dependent sources. That is little awkward. Let me make it little more neat. Still not correct. I don't know, sometimes I find it so difficult. It becomes freehand writing is much easier sometimes than taking perfect shapes from the app. Okay, so I have shown 2 dependent sources in L1, and I have to write my R2 back. I should not leave out any element in the process of rewriting the diagram. I will write R2 in my R2, then I'm done with that path, and I've got L2. So L2, again you have 2 symbols near L2, one being a rectangle and a dot. Okay, so I'll take it a little farther so that I can write the values conveniently, otherwise it becomes too cumbersome or too tiny for somebody to understand. Okay, so I'll try to write 2 sources again, 2 sources because of 2 symbols present. Okay, that is about L2. There is no more element there. I'll take L3 little farther, put L3. L3 also has 2 symbols indicating that it too has 2 mutually induced EMF, and there is a capacitor here. I'll extend these lines and draw a straight line. I need to take a source. There is another source. Alright, so I'm able to write the network. So let me put the values I will do one by one quickly. I suppose I need to put the currents. There is a current of I1 here, a current of I2 flows like this, a current of I3 flows like this. Alright, the three currents I'm able to put back. Then let me pick up the color yellow, because all my elements I'm writing it as, this is my R1, L1, this is L2, L3, this is capacitor C, and there is this resistance R2. Okay, so let me now pick one color by another and then try to do. I've taken this orange color which is near L1 and L2. Orange color circle is near L1 at the top and L2 at the top. Alright, so we are identifying either left to right or top to bottom. Okay, so L1 and L2 both have orange color dots at the top end of them. That means they are mutually coupled. That means current through L1 will produce an EMF in L2 and current through L2 will produce an EMF in L1. They are mutually induced EMFs. Alright, now we may have to find out the magnitude, we may have to find out the polarity. Alright, so I may need space. So what I mean is I'll clear this I2 for the time being. I'll write it a little later. Managing the space, I'll write the what do you call the rest of the things. That is much better. I'll remove this also. I'll manage the space. I'll write the currents later. Alright, so that shouldn't matter. It's there in the upper diagram. Okay, I'll write the values. Now I'll pick up the same color, L1. So L1 has got two mutually induced EMFs. One is for the dot. So L2, there is a current through L2. What is the magnitude of the current? So I2 minus I3 is entering the dot of L2. I suppose it's evident. This is L2. There is a current of I2 this way and there is a current of I3 this way. Okay, so top to bottom I2 is flowing, bottom to top I3 is flowing. So if I take the current as top to bottom, it has to be I2 minus I3. And this I2 minus I3 is entering the dot of L2. Alright, so that will produce a polarity which is at the positive end of the dot of the other coil. That is at the top end is positive. L1 has got dot at the top end. So positive, negative. What is the magnitude? So it's M12P. Have it written here? No. This should have been given. Maybe I have not written it while writing the problem. And this is M12P. Okay, this is I2 minus I3. Alright, so I2 minus I3 is the current that enters the dot at L2. Okay, that induced EMF is done. Now we may have to look at the other induced EMF, other mutually induced EMF. So the other mutually induced EMF is because of the triangle that is present near L1. Okay, so L1 has got a triangle, and for triangle I have chosen this purplish mava color. So this triangle is present here and another triangle is present here. Alright, that means in L1 there is going to be another mutually induced EMF when L3 carries a certain amount of current. It is a current dependent voltage source. Alright, so what is the magnitude of that mutual coupling? This has got a mutual coupling of M13. Okay, so if we talk about the magnitude, it's M13P. What is the magnitude of the current? I3 is the current that flows through L3. The polarity, I3 is leaving the dot. When I3 leaves the dot, it will produce a negative polarity at the similar dot of the coupled coil, and this has got negative at the top. So negative, positive. That's it. Alright. And there is we're done with L1. Now we'll come to L2. L2 has got one circle at the top and then one squarish symbol at the where is that color? I think, is this the color? I think this is the color I have taken. So there is L3 here, there is square here, and near L2 it is at the bottom. Alright, so now L2 is there, so we need to consider the mutually induced EMF at L2. One is for the dot. Dot is present near L1. Current through L1 will produce an EMF in L2. That's a mutually induced EMF. Okay. So what is the current? I1 minus I2 enters the dot at L1. So obviously if I start writing positive negative here, I'll use that color only. So that colors will make you understand that what are the things that we are referring to. So this is positive and this is negative. The coefficient of mutual coupling is M12P. The space is still insufficient, you see. This is M12P. M12P. The current I am considering is I1 minus I2. That is the mutually induced EMF. Now the other mutually induced EMF is due to this rectangle near L2 and rectangle near L3. So current through L3 will produce an EMF in L2. Okay, so current through L3 is I3. Okay, I3 leaves the dot. This will produce a negative sign at the dot, positive sign here, and this is M23P. I am going little faster, presuming that you are seeing my videos in sequence. If you see it in sequence, you will understand. Otherwise, maybe you may find it little faster. Okay, I would recommend you to, do things when you before you see the video, so that you would know whether you are able to do it on your own or not. Alright, now let's come back to L3 coil. In L3 coil, we have got a rectangle and a triangle. A rectangle is present near L2. Okay, that greenish thing. Okay, so current through L2 will produce an EMF in L3. Okay, so what is the magnitude of the current through L2? That is I2 minus I3 leaving the dot. I2 minus I3 would leave the dot. Okay, should we look at this? It's L2, there's a dot here, this is I2, this is I3. If I am talking about I2 minus I3, I mean this direction, current in this direction, and that current would leave the dot. It enters the undotted end, it leaves the dotted end. So this way it leaves, right? So I2 minus I3 leaves the dot. So when it leaves the dot, it will produce a negative polarity at the dot, which is at the bottom. Okay, so that is the polarity. Now what is the magnitude? So magnitude of that is, this is M23P I2 minus I3. Okay, now I'll go back to that purplish color. There's a triangle. The triangle is present in L1. L1 is carrying a current. What current is carried by L1? I1 minus I2 entering the triangle. Okay, so I1 minus I2 entering the triangle, okay, would produce a positive sign at the triangle. It's going to be like this. The mutually induced EMF is M13P I1 minus I2. We are done. Alright, so all we need to know is now write the equations. Now let me put back the current, Okay, I think it was this color. I'll write the currents here. Wherever I have my space, this is I1 I will write the, how do I write the current? Can I write the current this way? I2, this current is I3. Alright, the currents are there. So what I mean by P here, in every where I have used the operator P, what I mean by P is d by dt. And we know EMF induced, EMF in an inductor is L di by dt, which is a self-induced EMF, or it is M di by dt. If it is a mutually induced EMF, this is mutually induced EMF, this is self-induced EMF. And I have replaced this d by dt by P, so that my equations or my expressions appear simple and easy to write. Every time instead of writing d by dt, I'll write P. But then I need to make a mention. Then only it is acceptable, otherwise no, you cannot do that. Okay, so I will write here, d by dt is P. Okay, and then integral dt, I'll write it as 1 by P. I'll use this. Now writing the equations. Now it's simple. The problem is done, almost done. All you have to do is write the equations, rearrange, and then present in a desirable manner. Okay. So for mesh 1, writing the mesh equation for mesh 1. For mesh 1, I start from top left corner. How do I do? I normally start from this point, go like, and start from this point, go like this, come back. That's my path. Alright, so if I do that, I'll hit R1 first. So my equation is going to be R1I1. Then I am getting L1. I will write the self-inductance first. L1P, it's carrying a current of I1 minus I2 from top to bottom or clockwise direction. Then I may have to write the mutually induced EMF, which is my M12P, I2 minus I3. Alright. Then minus M13P into I3 plus R2 into I1 minus I2 equal to V of t. This is my first equation. I'll group all the terms. So grouping the terms containing I1, I will get R1 plus L1P plus R2 whole thing into I1. I'm grouping the terms containing I1 and the terms containing I2. I may have to group again. I will get it as minus L1P plus M12P minus R2 whole thing into I2. Terms containing I3 would be minus M12P minus M13P into I3 equal to V of t. Equation 1. Okay, you have 3 unknowns, so you need 3 equations. We are already done with first equation. So how do we write the second equation? In second equation, we come across L2 again in the clockwise direction. Mesh 2 from top left corner, I go in clockwise direction via L2, R2, L1 and back. Okay, so I have to write first the self-induced EMF, that is L2. I started writing d by dt. L2P into I2 minus I3 plus mutually induced EMFs M12P into I1 minus I2. Why it is positive? Because it's a drop in potential. I've hit the positive polarity first. So positive to negative, it was always drop in potential. Then I come across a gain in potential minus, that's M13P into I3 plus, oh, I'm sorry, I am a little sorry about this. This is M12P I1 minus I2 is alright. Then I come across another drop in potential plus M23P into I3 plus R2 into I2 minus I1. I'm writing for mesh 2, right? That's why. Plus M13P, because I'm dropping potential again, positive to negative, I3. Now negative to positive, minus, the magnitude is M12P, I2 minus I3 plus L1 P times I2 minus I1 equal to 0. Okay. Alright. So I may have to group the terms now. If I group the terms, what is it I get? I'll get the coefficients of I1 to be equal to M12P, I'll open up the parenthesis, M12P, alright, minus R2 minus R2, I'm grouping the terms containing coefficient of I1 minus L1P into I1. Okay, now let me group the terms containing I2. First term is L2P minus M12P plus R2 minus M12P plus L1P into I2. In fact, I might as well add these two and write it as 2M12P. I can do that. Alright, then plus terms containing I3 minus L2P plus M23P plus M13P plus M12P, I suppose, into I3 equal to 0. Okay, 2, 3, 4 terms. Alright, this is my equation 2. Okay, so now for mesh 3, I'll go for mesh 3. Mesh 3, how do we write the third equation? Again, we'll start from top left corner. What I mean is, I will start from here, go via L3, come via this source, second source, C, there is one more dependent source, another source, and L2. I'll do this way. That's my path. Okay, so I'll start from L3. Okay, so I'll start from L3, then go to this coefficient of M23 wala, this one, then I'll do this, sorry, L3, then this, C, and back. Alright, so now let me write. Okay, so my third equation is going to be L3P into I3. Okay, then I will have to write M23P plus M23P into I2 minus I3. Now I am coming the raise in potential M13P I1 minus I2. Now I am coming across a capacitor, so 1 by Cp into I3. Now I come to L2. I'll write the self-inductance, self-induced EMF first, that is L2P. The current it carries is I3 minus I2. I'm writing for the third mesh. minus, because raising potential, I'm hitting across a negative sign, M23P into I3 minus, again raising potential, hence the negative sign, 2P I1 minus I2 equal to 0. I have to group the terms now. I'll have to group the terms. If I group the terms, what I get is, I'm getting another. The terms that I get here is minus M13P then what other term I have, minus M12P, whole thing into I1, then group this I2 terms, M13P, rather M23P, then plus M13P, then minus L2P plus M12P, whole thing into I2, then the last term plus grouping the terms of I3, L3P minus M23P, then I have 1 by Cp, then plus L2P minus M23P, something into I3 equal to 0. We need to be a little cautious while writing the coefficients. Okay, subscripts and all these things, we need to be a little careful. If I can manage some space underneath, I'll be able to adjust. I will do some small I'm trying to accommodate the, adjust the space that I have. I suppose it's clear also. There is absolutely I'm trying to manage the space that I have, because I need to adjust within the available space. Just a moment, all right? I'll be able to take care of these things. Okay. Now I want to put it in matrix form. That is the only thing that I wanted to do. I need to manage the space. Okay. So I'll put everything in the matrix form now. Okay. So in vector matrix form, equation 1, 2 and 3 in vector matrix form is as under. Maybe I'll write it big and then shrink it. Alright, so all I have to do is take the coefficients. I'll open up the bracket, rather a square bracket I need here. Okay. Okay, so from equation 1, I have to pick up the coefficient of I1. Okay, that is R1, and open up the parenthesis, R1 plus L1P plus R2. Okay, that is the coefficient of I1. Then I have to take the coefficient of I2. Coefficient of I2, let me take a color, coefficient of I2 is now this is M12P minus L1P minus R2. This is coefficient of I2 from first equation, and coefficient of I3 from first equation is minus M12P minus M13P. Okay, I try to use the same white color, put it back like this, so that I can complete the first equation. What I mean is, I'll make them like matrices. Okay, so coefficient of I1, I2, I3 of first equation and arranged along the first row, and this is my I1, and on the right side we put the EMF V of t. First equation is completed. Okay, this is I1 and this is I2 and this is I3. That's how it is. Now from the second equation we will try to pick up the coefficient of I1 first. Again I'll take proper color. I will write it as, the coefficients are M12P minus L1P minus R2. Coefficient of I1 from second equation. Okay, so coefficient of I2, I'll try to take white. So this coefficient is L2P. Now I will add minus M12 and minus M12P. So that will be minus 2 M12P plus R2 plus L1P. These are the coefficients of I2 from the second equation. Now the third coefficient I need to write. Will I be able to manage space? And as alternatively, what I'll do is I'll remove this line. I'll have to manage the space, right? That is the hitch I have. You have to bear with me a little because of lack of space. Very close like this. Now I'll do this also a little. Shall I reduce it in size? Then take it closer. I suppose this is okay. Now I'll pick my white pencil back. So the coefficient of I3 from second equation, what is it? I will get it as, I'll use another color. Okay, there is a specific reason why I am writing it in specific colors. It will be evident in a short while from now. You have to be a little patient. That's it. And this is, minus L2P plus, it comes out of M23P because the drop in potential, or I'm taking the coefficients, right? I need not have to bother now. All I'm trying to do is mechanically I'm reproducing the coefficients that I've got in the equation. I'm getting this as M13P. Still the space is little. What do I do? 1 second. I'll shift it a little further like this. Now the last one is M13P. M13 and P. Close the bracket. With great difficulty. Okay, so now I'll come to the third equation. In third equation, I'll pick the same blue color which I have taken it earlier. The third equation has got the first coefficient, that is minus M13P minus M12P. This is the coefficient of I1. The coefficient of I2, I'll pick up this pinkish color, which is little gaudy, doesn't matter. This I may have to write it as L2P, the coefficient of I2, right? L2P, L2P minus M12P. Okay. Third equation, right? I'm looking at the second equation. All right. Okay, so this is minus this is M23P plus M13P minus L2P. Then what else is there? L2P then plus M12P. Okay, and the last element, again lack of space. What do I do? 1 second. It shouldn't matter because I've used distinctive colors, but still there has to be ample space. Okay, so now I'll pick white color, then I'll put the last element, the coefficient of I3 from the third equation. This is this big, right? I may have to write it as L3P, and then I will club the two, minus 2 M23P 1 by Cp plus L2P. Okay. I'll close the matrices. Okay, so we are able to write the equation in the vector matrix form, and of course the other things are 0, 0 here. So the first equation is, you can matrix multiplication, right? This into I1, this into I1 plus this into I2 plus this into I3 equal to V1. That's how we write the equation. Alright, so equation in vector matrix form is appearing to be of this nature. Now you inspect this, you look at this matrix, this impedance matrix. This is our impedance matrix. This is the impedance. You look at this impedance matrix. How do we identify the elements? The elements are identified as, I'll take a typical color, a different one, maybe this one. Okay, this is my Z11, Z12, Z13. Okay, first element, first row, this is impedance of second row and first element, impedance of second row and second element, impedance of second row and third element, impedance of third row and first element. This is 32, Z33. That's how we identify. If you can look at this, it is very, very clear by inspection. If we can match Z13 is equal to Z31, 12 equal to 21. You see slowly, term by term match. Then 23 is equal to 32. That's why I have taken similar colors, same colors. I have taken Z12 equal to Z21 and same color in yellow, 13 and 31 in blue, 23 and 32 in pink or magenta. Alright, so the off diagonal elements are distinct, but diagonal elements are distinct, and off diagonal elements have matching, like Z12 equal to Z21, 31 equal to 13, 32 equal to 23. So that completes the problem on mesh analysis, right? I suppose this problem is understood. Okay, so if this is understood, you can do similar problems. Okay, see you in the next video. Thank you.